Welcome to the deep dive. Today we're diving into something you might heard of, maybe even scratched your head over Einstein's theory of relativity.
Mm.
Don't worry, we're not aiming for a physics degree here.
Yeah.
We're using excerpts from the Feynman lectures on physics as our guide, and trust me, even Feynman knew how to make this stuff interesting.
Feynman had a real knack for finding the extraordinary in the seemingly ordinary.
Exactly. And today's deep dive is all about challenging what we think we know. Okay, so Newton's laws of motion, those seem pretty solid for a couple of centuries, right?
Yeah, for a good long while.
Turns out even the greats can be a little off.
It's true.
Yeah.
What's so fascinating is how even the tiniest discrepancy can unravel our whole understanding of the universe. It highlights how important it is to keep questioning assumptions, especially when we're dealing with something as fundamental as the nature of space and time.
Yeah, it's like finding a tiny crack in the foundation of a skyscraper. You might think it's just a small crack, but it could mean everything's about to change. So it wasn't like scientists were out there trying to find flaws in Newton's work, right?
Not at all.
Yeah.
It was more like they were encountering these puzzles they couldn't solve with the existing tools. For example, back in the late 19th century, they were really trying to understand light. They believed light, like sound waves, needed some kind of medium to travel through. They called this medium ether.
Okay, so ether wind, what exactly is that?
So imagine the Earth moving through this invisible ether, like a boat on a river.
Okay.
Scientists figured if this ether exists, we should be able to detect an ether wind, right? And that wind should affect how fast light travels, just like how the river current affects a boat's speed.
Makes sense.
Yeah,
So they set out to measure this equal wind, and that's where the Michelson-Morley experiment comes in.
precisely. The Michelson-Morley experiment was a stroke of genius. It was designed to be so precise that even the tiniest difference in the speed of light caused by this hypothetical ether wind would be detected.
It's like they built this incredibly sensitive cosmic speedometer, and the universe was about to throw them a curveball. So they're all set up, ready to measure the speed of light with and against this ether wind. What happens?
Well, their experiment was a masterpiece of precision, but the result, it was completely unexpected.
Yeah.
They found absolutely no difference in the speed of light, no matter which direction they pointed their instrument.
No ether wind at all. It's like setting up this elaborate trap and realizing you completely misunderstood what you were even hunting in the first place.
Exactly. It threw the entire scientific community for a loop. Because here was this elegant experiment, meticulously designed, and the results just contradicted everything they thought they knew about light and the universe.
And that's where Einstein enters the scene, right? Instead of trying to explain away the results, he completely rewrites the rules of the game.
Yeah. Exactly.
Yeah.
Einstein's genius was in accepting the experiment at face value. He essentially said, what if the speed of light is constant, no matter what? It seems counterintuitive, right? Like if you're on a moving train and throw a ball forward, it travels faster than if you were standing still, right?
Right.
But light, Einstein proposed, doesn't work that way. Its speed is a fundamental constant. It's like it's baked into the very fabric of the universe.
Okay, hold on. So if the speed of light is constant, but our measurements might change depending on whether we're moving or not, what's actually being affected? Don't tell me time.
You got it. That's exactly it. Einstein's answer was revolutionary. Time itself is relative. A clock on a spaceship moving close to the speed of light would actually tick slower compared to a clock here on Earth.
Whoa, wait, really? So you're saying time isn't this absolute unchanging thing that we experience it as? That messes with my head a bit.
It's definitely one of those concepts that bends your mind a little until you really wrap your head around it.
Yeah.
It's called time dilation, and it's honestly one of the strangest and most profound consequences of Einstein's theory.
Okay.
So imagine two identical clocks, one here on Earth and one on a spaceship, zipping through space at an incredible speed.
Oh.
From our perspective, the clock on the spaceship would appear to be ticking slower.
So for the astronauts on that spaceship, would time feel slower for them too?
That's the really mind-bending part.
Yeah.
They wouldn't experience time any differently. From their perspective, it's our clock back on Earth that seems to be running slow. It's all relative to the observer's frame of reference.
Okay, this is blowing my mind. But is there any actual proof of this? This all seems so theoretical.
Oh, there is. And it comes from those intriguing subatomic particles, muons, that Feynman talked about.
Muons.
Yeah, they're created high up in the atmosphere.
And even though they have a really short lifespan, we can detect them down here on Earth.
Hold on, how is that even possible? Wouldn't they just decay before they could travel that far? Are you telling me they're little cosmic speed demons breaking all the rules? Not quite, but they are taking advantage of time dilation. Because they're traveling at such high speeds, time is passing slower for them relative to us. So from our perspective, they live long enough to reach the Earth's surface, even though from their perspective, they only exist for a very short time.
So it's like they're getting this bonus time, a cosmic hall pass,
Uh,
because they're moving so fast. Okay, now that is seriously cool, and it actually proves that time dilation is a real thing, not just some mathematical quirk.
exactly. And this mind-bending concept of time being relative,
Hmm.
that's just the tip of the iceberg when it comes to understanding Einstein's universe. Remember that equation? CC.
I've heard of it, but honestly, I'm not sure I really understand what it means.
It's one of the most famous equations in history, but it represents something truly profound. It tells us that energy and mass are fundamentally connected. They're two sides of the same coin. A tiny amount of mass can be converted into a tremendous amount of energy and vice versa.
So, for example, the sun is constantly converting a tiny portion of its mass into this massive amount of energy that we feel as light and heat here on Earth.
Precisely. And here's where it gets really interesting. Remember we talked about how the muon's internal clock slows down because it's moving so fast? Well, that speed also means it has more energy. And EMC Carney tells us that this extra energy actually translates to an increase in the muon's mass, from our perspective at least.
Oh, wow.
It's this change in mass relative to us that contributes to the time dilation effect we observe.
Okay, wow. So we've gone from light needing a mysterious ether to time being relative to mass and energy being interchangeable. It's like we've tumbled down a rabbit hole of physics. This is definitely a deep dive. So we're talking about muons getting extra time, the sun turning mass into energy, and my brain is trying to keep up. But here's what I'm wondering. This is all incredibly cool, but how does it actually affect me in my everyday life? I mean, I'm not planning on hitching a ride on a muon anytime soon.
Right, it's a fair question. We don't directly experience these relativistic effects in our daily lives.
Right.
But even though it seems like science fiction, it has very real applications.
Okay, like what?
Take TPS, for example. Those satellites orbiting Earth, they have to account for time dilation to function accurately.
Well, really, you're saying my phone knows about Einstein?
In a way, yes.
Hmm.
Because those satellites are moving at high speeds relative to us, their clocks run slightly slower. We're talking nanoseconds, but it makes a difference. Without adjusting for this, GPS navigation would be wildly inaccurate.
So my phone is basically a tiny relativity machine. It's amazing how this seemingly abstract theory is actually built into the technology we use every day.
It really highlights how these discoveries weren't just about changing our understanding of the cosmos. They had practical implications that continue to shape our world. And beyond its practical applications, what's really incredible is how Einstein's theory completely changed the way we view space and time. They're not these rigid, absolute things as we perceive them, but they're intertwined and relative to the observer. It's like realizing the stage on which the universe plays out is much more complex and fascinating than we ever imagined.
So the next time I look up at the stars, I should be thinking that time isn't ticking at the same rate up there as it is down here. That is honestly a lot to process. And to think this is just scratching the surface of relativity, right?
Just the tip of the iceberg. Einstein's special theory of relativity, which we've been discussing, focuses on the relationship between space and time in the absence of gravity. But then there's his general theory of relativity, which brings gravity into the mix.
And that's a whole other deep dive for another time.
Precisely. But for now, I hope you walk away with a sense of awe at the elegant and often mind-bending nature of the universe we inhabit.
I definitely do. This was a journey, to say the least. Thanks for joining us on this deep dive into Einstein's theory of relativity. And remember, if everything appears to move slower at higher speeds, what would it be like to travel at the speed of light? Something to ponder. Until next time.